So I'm Shaun Crampton, a distinguished engineer at Tigera. How do I sum up my job? So I think my job is to make Calico as boring as possible. So Tomas has been making it interesting, adding exciting new features like BPF, and I do some of that too. But I really want to be this little emoji here, the little sleeping emoji, sleep in my bed at night. I don't want people calling me in the middle of the night saying their cluster's gone down. But scale has a way of making things interesting. So that's kind of what this talk is about. We had a couple of enterprise customers, this maybe about 18 months ago, and they were scaling up, and they were scaling up in a big way. And they were kind of scaling out of our performance envelope. So we've always claimed that we support whatever Kubernetes supports. At time of writing, I think that's 5,000 or 6,000 nodes. And we do occasionally test 5,000 nodes. It's part of our requirements for being in the cloud vendors, basically. So one of the cloud vendors provides us with cloud resources to be able to test for the scale that they support, and they've integrated Calico. And we had a couple of customers who were scaling up in different ways. So they were both enterprise customers, but nothing I'm going to talk about here is kind of enterprise specific. All of the improvements and enhancements we've made to address their problems have gone into open source because they're all in the kind of core of Calico. So one of them was scaling up their size of clusters. They were using federation. So when I say 11,000 nodes, they're using multiple clusters all federated together, but it doesn't make a difference from the scale point of view for the things I'm about to talk about. So they were effectively scaling up, to an 11,000 node cluster as far as some of our components were concerned. And then we had another customer that was pushing in a different direction. So they're like a big financial customer, and they have some of those important regulatory requirements. A long time ago, they have decided that the way they're going to separate their staging and prod environments is they're going to have an IPAM database for their entire network, and this CIDR is allowed to talk to that CIDR on these ports, and this CIDR is allowed to talk to that CIDR on those ports, and nothing else is allowed. And they keep track of that at a company-wide level. And they have a compliance requirement that every time they add a new technology, they add Kubernetes in this case, they distill that policy down and they apply it into the new technology. So they decided to drop 10,000 rules onto every pod in their cluster. And we don't put any hard limits in Calico, but we struggled with 10,000 rules on every single pod. And it was taking a while for the rules to render at start of day. So two kind of problems that prompted this talk. And I'm going to go through kind of three stages in the talk. The first, I'm going to talk about how Calico is designed to scale. That's a little bit of history, sort of paralleling what Utpal was talking about before, but more from a technical side. And where Tomas was talking about the data plane, BPF, I'm mainly talking about the control plane and the kind of brain of Calico that makes those policy decisions and that sort of stuff. I'm going to talk about the recent improvements to address those customers' pain points, and then I'll circle back to best practices. And it's kind of similar to what, was it Rui presented that? No, sorry. Jeremy presented that, yeah. So kind of motivating what he was talking about, really. So this is our original architecture. You have a Kubernetes cluster. You have, this was all the way back to Kubernetes 1.1. I think we aimed for, and I think we tested up to 1,000 nodes, 2,000 policies. We were aiming for 1,000 churns per second, like 1,000 pod updates per second. We kind of wanted headroom, and this was kind of where Kubernetes was at that point, like maximums that they could scale to. and 100 pods a node. That was just where Kubernetes was at the time. We weren't sure how fast users would adopt that high scale. As it turned out, most clusters for a long time were smaller than that. But we wanted to take on the high scale straight away and make sure that we were the obvious choice when people wanted to scale up. We used our own etcd for our data store. So Calico needs to store data. We need to know what the workloads are, the pods. We need to know what your policies are. We need to store IPAM data and that sort of stuff. And at this time, Kubernetes didn't have a place to store that. You couldn't store external data in Kubernetes at this time, so there was no custom resources. We settled on having an external etcd. The other component of Calico, or the key one for my talk, is Felix, which runs inside the Calico node daemon set. So Felix is our per host agent. And at that time, it was watching etcd and applying changes into the local data plane. So its job is to keep things in sync. A little bit more about Felix. So it concerns some of the enhancements I'm going to talk about. So our per host agent, we watch the data store. Felix gets a complete picture of the data store. So in the etcd days, it would download a full snapshot from etcd, parse it, and it keeps the data plane in sync. We try to make the changes minimal and atomic. So we move from one configured state to the next. And if we do get behind because we're processing lots of updates, we'll kind of skip ahead and do an atomic update. That's kind of what we try to guarantee. And I think we do guarantee that in all of the modes that I'm responsible for anyway. A key part of how it scales is it filters everything down early. So we're taking the full snapshot of the data store, which grows with the size of the data store, the number of pods, the number of policies, all that sort of stuff. In order to make that scale and do it on every node, we need to kind of put most of it to one side really quickly. So we ignore remote pods, we ignore policies that don't apply to local pods, and we put those aside, and then if later they do apply to a local pod, we kind of pull them back in and we apply them to the data plane again. So in general, we try to make sure that we scale with the locally active pods and policies, not the whole cluster, apart from this hopefully fast ingress stage where we sort of filter out what we need to filter out. How do we evolve our architecture over time? So CRDs came along, adding a second etcd to everyone's Kubernetes architecture. Not everyone is even deploying etcd kind of manually. They're getting it from somewhere else. They're deploying in the cloud, whatever. Asking everybody, manage an etcd, keep it backed up, do all the things you need to do. That was a bit of a headache, particularly back then when nobody knew what etcd was. Custom resources came along. So we ported the ported the control plane over to use custom resources and to directly watch Kubernetes instead of watching our etcd. We scale tested, and it wasn't great. So at 50 nodes, the API server started to show high CPU, and the CPU on our side wasn't great either. At 200 nodes, the API server was falling over, the Kubernetes API server. And the problem when we dug into it, and I'm really glad we scale tested this early and we had some scale goals. The problem was non-Calico resource updates. So if you want to know about every pod in the cluster, and we need to know some basic information about every pod in the cluster, we need to know its IP, we need to know its labels, you have to watch all the pods. And if you need to know about nodes to get their IPs or whatever else we need from the nodes, you watch the node resource. But there's lots of components that update those resources. So Calico updates the pod resource to add the IPAM information, and Calico updates the node resource to add our BGP AS number or whatever. But Kubelet also updates the node resource and the pod resource, and Kubelet updates the node resource every few seconds to check in and say, I've got this much CPU and I can schedule this much. And when you multiply all that up, the API server was handling I mean, for the sake of argument, kubelet updating every second. It doesn't really, it's more like every 30 seconds or something like that. But when you multiply it all up, the API server was having to process 1,000 updates a second and then fan them out to 1,000 nodes if you're at 1,000 node scale, talking 1 million updates per second or something ridiculous at the API server. That's why it fell over. The solution was to add a new component, and that brings us to our current architecture. So we added a component called Typha. If anyone's curious about the name, it's another name for the plant cat's tail, and I'll let you think about why that's appropriate. And so Typha basically does the job of watching the API server for all the Calico nodes. It watches the API server, caches in Calico format. It ignores irrelevant changes, so it ignores that CPU update from the kubelet. It ignores miscellaneous updates to the pods that we're not interested in. End result is that to the API server, Typha looks like a single Calico node used to look, and it can fan out to, I don't know, a few hundred nodes on the other side. So maybe you run 5 Typhas, you have 1,000 nodes. The API server doesn't bat an eye. It's a small load. Also reduces the number of events that we send down to Calico node and Felix. So Felix has less to do, and we save some CPU there as well. This sort of put us back in business with the new architecture, and through kind of incremental fixes and general improvements, both to Kubernetes client libraries, adopting new features of the Kubernetes client libraries mainly. We kind of kept it with Kubernetes scaling up to 5,000 nodes and above. So, what about the problems? So the first customer that I mentioned, their kind of effective cluster size was 11,000, and they were scaling up to 15,000. They were starting to see Felix take a long time to converge after a restart. They were starting to see Typha struggle a little bit. So we designed Typha expecting that everything would restart in the cluster at the same time, and we tested that scenario. So you have hundreds of Felixes connected to your Typha, and you kill them all, and they all restart, and they all thundering herd attack Typha, try to take it down. We designed for that, but we didn't design for that and scaling up the cluster past 5,000, past 10,000, up into 15,000 nodes. So we're starting to hit timeouts. No like hard limit on the number of resources we could handle, but we had network timeouts and things that weren't getting honored. They were also seeing like restarting nodes that were heavily burdened, failing their health checks because we didn't have enough CPU to handle the big influx of updates at the start. I don't think that's boring enough. So we made a bunch of improvements, and these flow back into open source. We tend to make improvements like this through open source and then flow them through into the enterprise product. It just makes sense for the core components. So these all dropped in Calico 325. Typha now shares the snapshot that it calculates when a new client connects between all the clients that connect at the same time. So that means if you have a thundering herd and 100 things all connect to Typha at exactly the same moment, we calculate one snapshot and send it all to all the clients in a binary format. We also compress the protocol. And when you put all that together, it means that instead of taking 3 seconds per client, which is kind of what we'd edged up to taking at these big scales, it's now taking 3 seconds to handle all of the clients that were connecting at the same time. So you have Felix connect, it waits 3 seconds to get all its data back that tells it everything it needs to know about the cluster, and all the clients that connect at the same time get exactly the same data at that same moment. So blasting blasting some binary data out to a lot of clients all in parallel is very straightforward to do and very efficient. We also decided that even though thundering herd is going to happen, and that's what we designed for, we just decided it's going to happen, so we designed for that from the off. We also added graceful shutdown to Typha so that in a graceful upgrade scenario, you have more headroom and things shut down more gracefully, and the load moves from one Typha to another more gracefully. We also improved our metrics, so Prometheus metrics for Typha and Felix, so that we could understand what was going on at these higher scales and generally give a better picture of what's going on inside Typha if you ever need to debug that. Part of the problem that first customer was having was to do with kind of policy multiplied by pod scale, and that kind of comes on to the second problem as well. So I'm going to talk about that. So the second customer, they have a huge amount of policy applied to every single pod, and it's all the same policy that applies to every pod. So it's this kind of segmentation policy. But it was causing trouble both in the control plane and the data plane to kind of calculate that policy. And the way Calico works, when you have a lot of shared policy like that, we calculate it once for everything that uses it. But if you have 10,000 things attached to every pod, we'll calculate it once and it might take a few seconds, 10 seconds, 30 seconds or something, if it's really big. And then we'll use it for all the pods. But if you have a scenario where your first pod drops on a node and 30 seconds is too long and it dies because it didn't get network connectivity, and then it gets deleted, we then tear down that policy and then we recalculate it. So they got in this nasty spiral, and we had to do something about that. Again, not boring enough. So after kind of, I don't know how long, 5-7 years of the architecture that we had for Felix's internals, which we call the calculation graph, it was time to optimize it. So when we were originally designing it, we chose the simplest algorithm that would meet the scale requirements at the time. It turned out that was good enough to scale up to 5,000 nodes. Wasn't good enough when you start adding 10,000 policies or policy rules on every pod. And it wasn't good enough when you're scaling up past 11,000 nodes and counting. So it was time to swap those simple algorithms that just do a linear scan through data structures to find what matches what selectors and that kind of thing, for some more complicated ones that optimize for the specific use cases. And it's not an exaggeration to say that with those optimizations in place, we saw a 60 times CPU and performance improvement in the calculation graph. It was taking a minute to apply this bulky policy and to calculate the very initial set of policy at those really big scales. And now it takes a second. So we've literally gone 60 times faster and, brought back all the headroom that we had at the much smaller scales where we were, testing to 1,000 nodes, but we kind of thought it will go to 2,000, testing to 5,000 and not seeing any problems, so it'll probably go to 10,000. Now we're at kind of 11,000 and it can go a bit higher. We did some testing that simulated the cases that these two customers were seeing, and we found some surprising bottlenecks as well. So the particular structure of that customer's policy meant that they had thousands and thousands of IP sets. Every one of their rules had an IP set associated with it. And it turned out that deleting IP sets was a bottleneck in the kernel. So it takes 40 milliseconds, which isn't a long time, but when you have 10,000, that's quite a lot. So we moved that to a background thread so it could just proceed in parallel with the other work in case you ever remove that policy again. And all this work went into Calico 3.27. So if you care about performance, and if you're at big scale, you want to be on 327 and above, or the enterprise versions that are based on that. And even if you're at small or medium scale, throw that one on and you'll see your CPU graphs for Calico node go, and they'll use, at small scale, probably half as much CPU, at medium scale, 10 times less, at really big scale, 60 times less. So it's a really big win. We've got another small enhancement in 328. So if you have lots and lots and lots of policies on all your pods, but if they're all the same, the IP tables chains we were programming just to jump to the policies get quite big. So we have a policy chain, we have an IP tables chain per pod, and it will jump to policy 1, and jump to policy 2, and jump to policy 3. And if you have 250 policies on your pod, that's 250 jump rules, which starts to add up if every pod has 250 of those. So we now have a kind of intermediate kind of indirection when that happens. And if you have lots of shared policies, we'll render another chain that they all jump to, and that has 250 jump rules in it. So that makes the IP tables rendering quite a lot more efficient if you're in one of these scenarios. Particularly if all of your policies are small. If you have one rule in each policy, you're kind of duplicating all the size of the rules. I wanted to talk a little bit about how we're now testing to these scales, because it's getting really difficult, to be frank. We can do a 100-node scale test, no problem. We can spin that up in an hour. We can do an occasional 1,000-node scale test without breaking the bank, and we can do maybe a 5,000-node scale test if one of the cloud providers gives us some resource to say that, here's a cluster, run it on it. And we have a tool that we use for stressing it. But to test these scenarios, we kind of need to go beyond that. So we've started building out a simulated scale testing infrastructure that allows us to run mock Calico nodes and mock kubelets. So if you look in like kubectl, you would see 1,000 nodes on your cluster. You would also see 1,000 pods on your cluster, and each of those pods would actually be running a kubelet inside. So that the mock kubelet is called Mocklet. It's an off-the-shelf open source project that we pulled in, and we made a nobbled version of Calico node that does the data store operations without doing any data plane operations. You can then run mock pods on those nodes, and they get a taint in Kubernetes terms. So normal pods won't run on them, but you can schedule things onto them deliberately to simulate having lots of pods in your cluster. And with those, we can easily spin up a cluster that looks like it has 1,000 nodes on it. We can easily put 100,000 pods on it with no problem. And then we could go even higher, but it starts to take a while to spin one up. So for this testing, we actually abused the Calico Enterprise Federation feature. So we can connect one cluster to another cluster that has a lot of mock workloads in it. But instead of connecting it once, we can connect it 50 times. And then whatever you do in the mock cluster shows up as 50 times as many things when you look at it from the other cluster. So this is how we scale tested for the 11,000 node case. And it actually makes it brutal because we've got 50 connections open instead of one. And then every time anything changes in that mock cluster, we see 50 updates barreling in instead of just one. So you get a very lumpy load. It's great for stressing and making everything miserable, but we can handle it. So I said we beefed up our dashboards, our metrics. So we've been working on some Grafana dashboards for monitoring Calico. So the one on the right is for monitoring Taifa. So I built that myself as I was doing the scale testing. I think we just put up a pull request to the Calico docs to put that in there. So Reza helped me get that into the docs. I don't think it's quite gone live yet, but I built that dashboard with kind of internal knowledge about what I'm expecting to see in there and put alerts and things on it that will kind of flag if Taifa's not happy. And then we've got the other one on there, which we've had for a while, which is monitoring Felix. So both of those are in our docs now, and you can install them into your cluster to monitor our components efficiently. And yeah, that's what I was using to test the really high scale. Best practices, I'm just going to reiterate what Jeremy was saying earlier. So Calico now has headroom. So if you're at small scale and you plan to stay there, you probably don't need to worry. But if you do think you might scale up, you want to design your policies using the best practices, design the way you're using Calico with the best practices. It's very, very hard to change your policy like templates and your ingrained company knowledge of how you build policies. Like as you scale up, you want to get it as right as you can to start with. We have some headroom, so I cranked it up as high as I could until the wheels fell off, and it was something like 3 million pods before it started to really struggle. Big caveat there, it was using a lot of RAM to do that. So I think that's probably the next scale issue that I would like to work on, is if you do go to these like really big scales, like if you throw 1 million pods in there, Typha uses more RAM than I would like, and Felix uses a bit more RAM than I would like, even though they're not using much CPU. So I'd like to tackle that. But yeah, I did get it up to 3 million pods, and it was quite a sight. So best practices overall, do run Typha. It reduces the load on your API server, even if you're in a smallish cluster. As soon as you've got more than 5 nodes, really, it reduces the load and generally speeds things up. Use the Calico operator to deploy Typha. You can do it manually with manifests, but they don't set up the TLS for you automatically, because we can't do that in a manifest. But the Calico operator will set up TLS between Felix and Typha and just generally secure everything properly for you. It also auto-scales Typha according to the size of your cluster, so you kind of install it and set it and forget it. Use the dashboards in our docs, and we're improving those all the time. And finally, the policy scales best when you make use of the early filter that I was talking about. So that's where the recommendations came from in the previous talk. So the general idea is you want to minimize the active policy on each node as much as possible. So do use the top level policy selector. And if you have a namespaced policy, then it has an inbuilt top level selector, which is like the namespace that it's in. So you kind of get a big chunk of that already. But do use that top level selector to constrain what pods your policy applies to. Don't use a source selector in an egress rule, because it's redundant, but it does get calculated and it gets applied in the data plane. So if you have the correct like policy selector, and that's telling Calico, apply this policy to this pod, then you don't also need a source selector in your egress rule saying, this rule applies to these pods, because you've already told it to apply the policy to those pods, but we will render it, and that makes that is extra work that we just don't need to do. Whereas if you use the top level selector, then it hits that early filter and it gets put to one side, and it has basically 0 CPU cost to have those extra policies in there, and will only activate the policies on the particular nodes where they're needed. So use that, and that really plays to our strengths. For exactly the same reason, you don't want a destination selector in an ingress rule, because again, you've already chosen where the policy applies. So use that feature, not the one in the rule. The reason that we allow those things in rules is because we have an exotic type of policy that I don't expect anyone to use. Here it's quite niche, but we have an apply on forward policy, which allows you to run Calico on a gateway that's between two things, whatever, two parts of your network. And then you might want, your gateway isn't running any pods, it's just applying policy that needs to have sources and dests. So it's a little bit of we probably shouldn't have let that go through into the normal policy, but it's there now, so we can't just rip it out. But strongly recommend you don't do that. And help the data plane. If you combine rules that all have the same policy selector into the same policy, that's more efficient. It all kind of goes through the chain as like one blob, and then we program one IP tables chain or one set of BPF policy or whatever at the end of the day. And that's just a bit more efficient than having, one rule in each policy. And if you have more than a handful of CIDRs in your rule, switch to using a network set, and then your packet path will be more efficient, because we'll render one rule that says, check this IP set to see if it's in there, instead of rendering lots of rules, each with a single CIDR in it. And that's just we don't have an optimization that spots if you have lots of CIDRs in a rule and automatically does that. But if you use a network set, you can get better performance. If you do want to see what IP tables rule or what BPF code popped out from this particular policy rule, we have a feature for a while that lets you put an annotation on a rule. So you can just annotate it with foo or whatever you want to call it. And that will pop out verbatim into the data plane. So when you look at your IP tables rules, you can see a comment that will say, this is rule whatever. And you can see exactly what we turned it into. So that's helpful if you don't want to kind of go through all the Calico code and understand exactly what we're doing. You can still just home in on a rule that you care about. And that's it. Yeah, so kind of reiterating what Jeremy said earlier.